Hi everyone, in this last lesson on utility, we're gonna talk about how we design common frequent utility systems. Steam systems are a very common heating utility. We use it up to high temperature, but not too much because near the critical point the heat carrying capacity becomes less and the pressure becomes too high. Frequently we find systems with several levels at different pressures: low, medium, high, very high pressure, where the denomination is not standard, in order to increase the efficiency and cost, because when we use the heat at the precise level, we are increasing the efficiency or not wasting useful levels of energy. Steam systems are very different. In the figure you can see a complete system with preheating of boiler feed water to produce a high pressure steam. This is directly used to heat the system, while other parts produce work over back pressure turbines, finishing an intermediate medium pressure or a final low pressure steam that are used to heat the system at different levels, or through a condensing turbine without producing a steam but a liquid and get out most of the shaft work. The different condensate then return to the preheating and the boiler. Well, design from an energy thermodynamic point of view is easily done in the grand composite curve diagram, so we can minimize level temperature or maximize flows at low level, that is a normal practice, or explore different combination or alternatives levels and quantities of steam. The behavior of this steam system, the steam mains set, is very complex, and the complexity increases with the number of levels. It is not normal to see more than 4 levels of steam. Furnaces that are used in cases of very high temperature or large duties. Furnaces are very complex systems. Here we explore a simplified model, with the flue gases losing heat linearly with MCP from the adiabatic flame level of temperature to stack temperature. This is not real because the real T is less than the flame T because of radical formation, broken molecules, and of excess air. But as its temperatures are very high, normally is precise enough to make the calculation. As the slope is greater or the change in level of temperature is greater, then you profit better of the heat in the flue gases, and you net less fuel to produce it. This is limited by the process pinch, the utility pinch, if flue gases touches the grand composite curve of the process, or acid condensation, the phenomenon of acid stack. Besides, the straight line model informs also of the heat loss to the atmosphere from the outlet temperature to the ambient temperature. Thermal oil systems are very similar to furnaces, but the heat transfer is from liquids normally at high temperature, not so high as flue gases, and not constant with a certain slope. We want also to minimize the slope in order to reduce the mass flow rate of oil. The final cooling temperature of the oil is limited by the process pinch or the utility pinch. It is the utility touching the process curve. It is not rare to see oils condensing changing phase. It substitutes steam for transferring heat with good heat transfer coefficient, condensing one, at very high temperature. Low temperature or subambient cooling. This is normally an expensive utility because for vapor compression it works with mechanical power. It can be done at constant T when a pure compound is boiling, or changing temperature when a mixed refrigerant is used for heat removal. Like with the steam system, it's very normal to use several pressure temperature levels to maximize efficiency, cooling the system, the process, at different levels. This made for very complex design that are normally well carried out in the grand composite curve. Like with the steam, you can explore different levels and optimize your system for shaft work, for mechanical power or electricity, not minimizing heat flows. And then cooling water or other cooling with changing temperature, because air-cooled exchanger or combustion air preheating are similar. In the grand composite curve, we can explore amounts, heat flows, and levels of temperature, getting the mass flow rate for the reverse of the slope. And finally, thermal engines and heat pumps. For topping cycles, like gas turbine, that gives heat to the process, is used as heating, this heat output must be produced above the bench as heating. But for bottoming cycle, like organic Rankine cycles, that produce work from residual heat from the process, this heat must be taken from below the bench as cooling. And for heat pumps that are difficult to place, they must take heat from below the bench and give it up above the bench. For heat pumps, the smaller the difference in temperature, the better, because in practice it cannot be very wide. This made this type of big nose processes adequate for this utility. And remember that following the first law, the heat output above the bench must equal the heat input plus the shaft work employed in raising the level. And this is all for common utility design.